So let's
Yes,
start.
sir.
I
You
hope
can
my
please
screen is
proceed. Yeah.
visible. Okay. I hope my screen is visible.
Yes, sir. Your screen is visible.
So good evening everyone. My name is Pratik Bansal and I am an application engineer in integrating microsystem. I welcome you all in day one lecture session of Synopsys Simple Software. And today I'll be presenting on the topic of applications of 3D modeling in orthopedics using Synopsys Simple Software. So this presentation is on behalf of integrating application actually involved. So let's begin with introduction. Orthopedics as a discipline relies heavily on the imaging techniques. Okay. So let's begin with introduction to orthopedic imaging and segmentation. Orthopedics as a discipline relies heavily on imaging techniques for diagnosis, planning, and treatment. In clinical orthopedics, we often deal with complex anatomical structures such as bones, joints, ligaments, and cartilages. Segmentation is the process of isolating specific anatomical structures from medical images, enabling doctors and engineers to create 3D models that are highly accurate and patient. For example, when preparing for a total hip replacement, it is crucial to segment the pelvis and femur in the CT scan to design a well-fitting implant. This can also be extended to applications such as pre-operative planning and custom implant design. Segmentation also forms the foundation for simulations like finite element analysis or conditional dynamics, allowing biomedical engineers to study stress distribution and fluid interactions in orthopedic implants. Synopsys simplifies this entire process by offering a user-friendly interface and powerful tools that automate and assist segmentation, ensuring the models generated are both reliable and clinically useful.
Pratik, can you change your microphone? Your voice is not properly audible.
Sure, sure,
Just
sure.
echo.
Aish, I also hope you are recording the session.
Hello, am I audible now?
Yeah, it's way better.
Thanks.
Uh, I also hope you are recording the session.
Yes, yes, we are recording the session. Yes.
So let's
Imaging processing basics.
medical imaging.
Modeling or simulation tasks in orthopedics. Among the most common imaging modalities are like CT and MRI scans. CT or computed tomography is specifically useful for visualizing bone due to its excellent contrast and spatial resolution.
MRI or magnetic resonance imaging, on the other hand, excels in visualizing soft tissues like ligaments.
And tendon
Each image
modalities produce
the form of voxels, which are essentially 3D pixels. The intensity of each voxels, particularly in CT, is measured in how CT responds to tissue.
For instance, cortical bone has a high H value.
Soft tissues and air have lower values. However, noise, and incomplete slices, especially in regions where there is patient movement on metallic implants. This makes it essential to pre-process images before
Tools that
removal tool and
This ensures
that the image fed into segmentation modeling pipeline is of the highest possible quality, making subsequent steps more efficient. Understanding these basics is crucial to maximize Simpleware's potential. Let's coming to the quick recap of Synopsys Simpleware software. Before we move into specific of orthopedic applications, Simpleware is an integrated software suite designed to process and visualize 3D image data acquired from modalities like
what makes it especially powerful is its capability to segment and model complex anatomical structures with a high level of precision. It is used not only by
but also in
the strength
software lies in its comprehensive toolbox, which includes tools for resampling, cropping, segmentation, surface, and volume meshing, and even automatic segmentation modules powered by machine learning. Furthermore, its compatibility with simulation platforms like ANSYS, COMSOL, and Abacus, and design platforms like SolidWorks makes it all-in-one solution. Whether you are planning a surgical implant or preparing a mesh for finite element analysis, Simpleware ensures the transition from imaging data to engineering or clinical insight is as smooth as accurate as possible. It's powerful software that is both user-friendly and highly customizable for different user needs. Let's coming towards the tools. Synopsys Simpleware is packed with a variety of tools designed to handle each step of the modeling workflow, from initial image processing to final model export. The core set of tools includes resample, crop, transform, segmentation toolkit, surface tools, and volume mesh tools. Each of these plays a specific role. Once segmentation is done, the software provides tools for smoothing, filling gaps, and preparing models for export. Measurement tools allow one software validation and 3D preview and 3D printing tools. Makes it easier to access model accuracy visually. Whether you're a radiologist, engineer, or surgeon, Simpleware's toolbox is designed to make your workflow intuitive and efficient. Now let's get it deeper into the tools. So pre-processing is an essential step in the workflow, and Simpleware offers robust tool to make this both flexible and efficient. The resample tool is used when the scan resolution is either too high for memory or needs to be standardized. By adjusting voxel resolution, we ensure that the image retains surface anatomical detail while improving performance for segmentation and analysis. In scenarios where we receive extremely high resolution micro CT scans, resampling helps in making the dataset manageable without compromising the fidelity of the critical features. Similarly, the crop tool helps in focusing only the region of interest. For instance, when working with pelvic data, we want to isolate the acetabular region to study hip joint pathologies. Cropping reduces the file size and eliminates unnecessary noise from the rest of the image. Both of these tools work in 2D viewer and 3D viewer, providing both flexibility and precision. In addition to resample and crop tool, the transform toolkit allows user to rescale, pad, or align images, ensuring the data is aligned in consistent anatomical orientation. These tools serve as a foundation before initiating segmentation or exporting data for simulation or design. Now coming to the segmentation tools. Segmentation is where the imaging data begins to take shape into meaningful anatomical models. One of the foundation tools in Simpleware segmentation suite is threshold tool. This tool allows users to isolate structure based on voxel intensities, which is especially effective in CT imaging. For example, bone typically has Hounsine units above 200 HU. By applying a threshold at this level, we can automatically extract the bony structure from surrounding soft tissues or air. The result is a binary mask that highlights only the voxels within the second selected intensity range. This is fast and efficient way to segment structures like femur, tibia, and hip bones. Once thresholding is done, manual refinement often becomes necessary, especially in areas where the scan quality is inconsistent or where multiple structures are closely packed. This is where 3D editing tools come in. Using the lasso tool or the freeform selection tools, users can manually erase unwanted areas or refine boundaries directly in the 3D view. This interactive editing environment makes it easier to clean up segmented structures, especially around joints or in case of osteophysics and deformities. These editing tools bridge the gap between automated processes and clinical precision, allowing for creation of highly accurate and patient-specific models suitable for further analysis or surgical planning. Coming next into segmentation tools. After the basic segmentation tools, further refinement is often needed to isolate individual anatomical structure. One of the best efficient tools in this context is the mask flood fill. This tool allows users to clean up segmented masks by removing small disconnected regions or islands that are not of interest. With just one click, SimpleWay retains the largest connected region within the active mask and discards smaller irrelevant components. This is particularly useful in scans where noise or calcification generate scattered regions that might otherwise interfere with downstream applications. Another power tool is split region. When dealing with complex anatomical assemblies such as pelvis, femur, and sacrum, these structures are often closely attached in the scan. The split region tool uses a watershed algorithm to automatically separate these into distinct parts based on local intensity minima. Each region is then color coded for easy identification. This not only saves time but ensures consistency across different data sets. Finally, Smart Paint is a semi-automated manual painting tool that enhances users' ability to fine-tune boundaries. It uses adaptive region drawing techniques, allowing the user to add or subtract from a mask by brushing over targeted areas. It's like a balance between manual control and automated assistance, making it an essential tool in complex or irregular segmentation cases. Coming towards additional tools, once the primary segmentation is completed, the next step is to clean and enhance the segmented structure to make them suitable for modeling or simulation. Synopsys Simpleware provides several additional tools for this. One of the most frequently used is bone filling. This tool addresses issues caused by scan limitations such as small holes or discontinuities in the segmented bone geometry. It works by interpolating missing data to ensure the model is watertight and structurally consistent. The recursive Gaussian filter is another powerful feature that helps smoothen surface artifacts. In medical imaging, stair-step artifacts can occur due to slice resolution. This filter applies Gaussian smoothing in three dimensions, refining the mask or surface to make it more naturally and visibly accurate without blurring critical features. Other tools include cavity fill, fill gaps, and island removal. Cavity fills help close internal voids in the bone structure that are not psychological or artifacts of poor scan quality. Fill gaps smooth out small discontinued voids, and island removal deletes objects smaller than specified threshold, ensuring only clinically relevant structure remains. Collectively, these tools prepare the segmented model for robust simulation or printing workflows and ensure no manual post-processing is required in CAD or finite element analysis tools. Coming towards automated segmentation, Simpleware includes specialized automated segmentation modules known as AS Auth module. These modules are powerful by machine learning and are trained on a broad set of anatomical data, making them highly effective for routine orthopedic tasks. These modules are available for key anatomical regions such as hip, knee, spine, ankle, shoulder, and craniomaxillofacial areas. What makes these tools invaluable is their ability to dramatically reduce the time and variability associated with manual segmentation. For example, the AS Ortho Hip CT module can automatically segment structures like proximal femurs, pelvis, and sacrum. Similarly, the knee CT and knee MRI modules can segment femur, tibia, patella, and associated cartilage and menisci. These tools not only isolates the bone but also place anatomical landmarks that are critical for implant planning and biomechanical analysis. With these automated segmentations, user can go from raw DECOM data to simulation-ready models within minutes. This has transformative implications in clinical workflows, medical device research and development, and academic research. In short, the AS Author suite makes segmentation faster, more consistent, and scalable, especially for users working with large datasets or multiple patient cases. Next, the backbone of automated segmentation modules is simpleware integration of machine learning algorithms. Traditional segmentation workflows are often labor intensive, require skilled personnel, and extensive manual intervention. However, the inclusion of AI based tools allow simpleware to deliver fast, accurate, and reproducible results. These machine learning algorithms are trained on a wide range of anatomical scans and validated against ground truth models. What differentiates Synopsys Simpleware's approach is its emphasis on generalization and reliability. The algorithm can process CT and MRI scans across different scanners, resolutions, and patient anatomies with minimal setup. In many clinical and research and development environments, batch processing of multiple datasets is necessary. Simpleware supports batch workflows allowing users to run automated segmentation on dozens or even hundreds of scans in a fraction of time it would take manually. Additionally, these AI tools reduce intra and interoperative variability, which is crucial for studying requiring consistency. By freezing up time from repetitive manual tasks, engineers and doctors can focus more on interpretation, analysis, and decision making. The result is a faster and more efficient workflow that maintains high levels of anatomical accuracy. Let's now look more closely at the anatomy specific features of AS ortho modules. When working with hip segmentation using CT scans, the module extracts the proximal femur, pelvis, and sacrum. Additionally, it identifies the places anatomical landmarks such as anterior, superior, iliac, spine, pubic symphysis, and sacral promontory. These landmarks are essential for accurate implant alignment, pelvic tilt assessment, and biomedical simulation. For knees, especially using PD weight MRI scan, the software segments structures like the femur, tibia, patella, fibula, and also isolates cartilage regions. This is vital for assessing joint degeneration, designing custom implants, or planning surgery such as total knee replacement. Furthermore, the module places landmarks at critical points such as femoral and tibial tuberosity. These anatomical features are key for patient-specific measurements and guide the positioning of cutting guides and jigs. This kind of targeted segmentation enables doctors and researchers to analyze, measure, and simulate joint behavior with precision. It not only saves time but also improves clinical utility of model generated. These features make simpleware ideal for orthopedic department, sports medicine clinics, and implant manufacturers. To summarize, the AS Ortho module in Simpleware is dedicated auto segmentation solution for orthopedic applications. It brings together the power of machine learning, anatomical intelligence, and workflow automation to address the time-consuming nature of traditional segmentation methods. One of the greatest advantages is that users do not require advanced training in imaging software or manual segmentation techniques. The software guides user through a step-by-step process where they can select the anatomical region, import the image, and generate the segmentation with a single click. These capabilities are especially valuable in settings where time is critical, such as surgical planning, device prototyping, or large-scale clinical studies. For example, a hospital can use AS Ortho to rapidly prepare anatomical model for 10 hip surgeries scheduled in a week. The consistency and accuracy achieved using AS module ensure that each case is handled with the same rigor even with different personnel involved. Moreover, the software allows minor manual adjustment if needed, ensuring flexibility without compromising the automated efficiency. By offering repeatable, validated workflows, AS also reduces human error, improves reproducibility, and enhances confidence in downstream modeling, simulation, or fabrication process. One of the key benefits of using Synopsys Simpleware in orthopedics is its seamless integration with CAD software, particularly in SolidWorks. This integration is enabled through a dedicated module called Simpleware Designing, which allows user to transfer data back and forth between Simpleware and SolidWorks without needing to export and import files manually. This kind of interoperability streamlines workflows dramatically, especially in the field of implant design where iterative processes are common. Let's say biomedical engineer is working on designing a custom acetabulate cup for hip replacement. The 3D anatomical model is generated in Simpleware from a CT scan. Using the design link, this model can be directly brought into SolidWorks where the implant can be redesigned. Once the design is complete, the implant can be sent back to Synopsys Simpleware for evaluation in the anatomical context, verifying fit, alignment, and position. This live bidirectional data exchange minimizes data loss, improves accuracy, and reduces turnaround time. Furthermore, device link support updates with a single click. If changes are made to anatomical model to implant, both environments can be synchronized immediately. This dynamic connectivity empowers engineers and doctors to carry out patient-specific implant design, surgical planning, and iterative testing much faster than traditional segmented workflows. After importing a surface model, such as implant, into Simpleware, the next critical step is its accurate placement within the anatomical data. Simpleware provides a comprehensive suite of surface tools designed specifically for this purpose. These tool ensures that imported implant fits precisely within the 3D model of the anatomy, aiding in implant fitting, simulation, and preoperative planning. The first tool to be used, zero precision, which automatically centers the implant geometry based on all three axes. This ensures a neutral starting point from which further alignment can be done. Next, register datasets allow positioning for implant relative to anatomical features of the model. For example, when positioning an acetabular cup into segmented pelvis, this tool helps align the implant to desired surgical axis. Once roughly positioned, the position of orientation tools fine-tuning capabilities. Users can manually rotate, translate, or snap the implant into exact alignment using anatomical landmarks or grid systems. These adjustments can be visualized in both 2D and 3D views, ensuring a precise and intuitive workflows. This process is particularly useful when validating whether a particular implant design will accommodate individual anatomical variability or pathologies like deformities. Altogether, these tools play a vital role in implant positioning accuracy, design validation, and surgical rehearsals. Now coming to Synopsys Simpleware import formats, it supports wide variety of image import formats, making it compatible with virtually all common medical industrial imaging systems. This ensures that no matter where the imaging data comes from, it can be seamlessly integrated into modeling and simulation pipeline. In the medical domain, Simpleware supports DICOM, known as digital imaging and communication in medicine, which is standard format for radiological imaging such as CT scan, MRI scan, micro CT scan. DICOM is used for industrial images. It is also supported. Users can also import 2D images text, including BMP, JPEG, TIFF, PNG, and GIF, which are often used in research or non-clinical imaging applications. The level of flexibility allows simpleware to be used not just in orthopedics but in cardiology, neurology, oncology, and even material science. Whether the goal is creating anatomical models, visualizing implants, preparing data for simulation, simpleware robust import capabilities serve as the first critical step in 3D modeling journey. Once the segmentation and modeling processes are complete, the next step is to import the results for visualization, design simulation, or fabrication. Synopsys Simpleware supports an extensive range of export formats to cater to various downstream applications. These exports include surface models, volume meshes, and even high quality renderings and animations. For CAD applications, users can export model in STL, etc. These are widely accepted formats in most design environments, including SolidWorks and AutoCAD. For simulation, the software supports exporting to Abacus, ANSYS, COMSOL, and Nastran formats, complete with nodes, element types, layers, contact surface, and material properties. For visualization, 2D and 3D screenshots can be exported as PNG, JPG, BMP, or even vector graphics like EPS and PDF. A particularly unique feature is the ability to generate virtual X-rays and export 3D PDFs for surgical planning or education. This robust export system ensures that users can take full advantage of the segmented and modeled data in virtually any downstream platform for simulation, reporting, and collaboration, editing, manufacturing. Now, Simpleware FE is a specialized module that allows users to generate finite element analysis and computational fluid dynamics models directly from segmented image data. What makes Simpleware FE exceptionally it is ability to create simulation ready meshes that do not require additional cleanup or remeshing in external software. This saves both time and effort for researchers and engineers working in simulation heavy workflows. Using volume and surface meshing tools, users can create high quality hexahedral and tetrahedral meshes with smooth transitions and well defined boundaries. These meshes can be assigned region specific material properties directly from the intensity values of the original scans or from user defined presets. This is particularly useful in orthopedics where bone density plays a crucial role in simulation accuracy. Simpleware FE also provides options to define node sets, contact regions, boundary conditions, and support for anisotropic material properties. Once the model is meshed and configured, it can be exported to all major solvers including Abacus, ANSYS, COMSOL, LS-DYNA, and others. This level of automation and integration ensures that simulation projects can begin with highly accurate, anatomical faithful models, reducing assumptions and improving the fidelity of the results. So now let's coming towards the live demonstration.
Hi, before starting the live demonstration. I just need to know that if anyone has worked in the field of medical image processing or have used any software or have used Simpleware in past. So, does any participants have a knowledge of this image-based modeling software? They can let me know.
Yes. Ayush, if you can. Uh, so hi,
So
this is.
this is our starting window.
Sorry, can you hear me?
Pratik, could you please wait? Pratik, could you please wait? I'm
It
just
takes some time to check the license.
Pratik.
Madam, you can go on. Ayush,
Pratik here.
Dr. Rupsa, madam was
After
answering your
initializing,
question. Ayush, can you hear us?
Yes, Srinath, sir, I can hear you.
And sorry, I was about to say Dr. Rupsa was answering to your query.
Yeah, yes, ma'am.
Yes, Ayush, so good to see you. So, I.
Pardon, ma'am, your voice is cracking up.
Okay, can you hear me now? Can you hear me well?
Yes, ma'am, I can hear you.
Okay, awesome. Let me know if you can. So I joined about 3 years back. I'm a faculty here, assistant
Okay.
professor. Uh, So 4 years, all my postdoc, mostly I have used CTs, MRs, knee imaging, hip imaging, all that you have shown. So I'm really pleased to see the whole platform. It really makes things easier. I do have a few questions if you have, or we can take those questions later as well, if that's okay.
Then whichever is feasible. So, have you used any software? Any specific
So
software?
we designed our segmentation algorithms on our own. So we
Okay.
trained models, but we have used ITK Snap and we have used
Okay.
like the MD.ai, where our clinicians would go and make those masks manually, which were then exported and we trained model to do the segmentations.
Yeah, like UNet models that you had worked on. Yeah, I understand.
Foundation models,
Yes.
medical.
Yes.
med segmentation models, med SAMs, and all of that.
So, ma'am, since this software is already with you, so you have the access of the software, I guess.
Mm-hmm.
We also have one more new feature that has been introduced in the latest version. That is the feature of external models. So even if we are having our own set of segmentation algorithm and we need to do the benchmarking of that algorithm, so that can be done.
Right.
We can use a dice score calculator. That's the mass similarity calculator tool that it has named, and it basically works on dice score principle to calculate the similarity between two different mass. So even if we are having our own sets of segmentation algorithm, that too can be integrated. And apart from that, Monai models you must be aware of by NVIDIA,
So,
that can be integrated, and total segmenter from 3D slicer you must have heard of, that too can be also integrated. So there are multiple external models that have been included.
okay, so that was one of my questions. That what exactly is? Do you have like a paper or a white paper, which we can look? So we're using the software to create our own masks, and we have to sort of refer to a paper. So if you could share any of the white papers that has been used, would be great. Um, and then my other question that will also kind of get answered in that white paper is that what is the sort of accuracy and what are the dice scores that you
Yes.
this
So,
process?
ma'am, to answer that, we do have white papers. I'll be sharing the link with you for that.
Sure.
And the second, the accuracy. So, in that white paper, the accuracy came out to be around 97 to 98% using the
Mhm.
auto segmentation algorithm for a non-diseased data set. For a diseased data set, it is much more lesser, so we need to rely on manual segmentation more because if there's a tumor that is present, so the software is pre-trained on the basic data set, and it faces difficulty in finding certain defects. So
Yeah,
in that case, we need to use the manual segmentation and another
that-
other algorithm like external models.
sure. But then also, disease data set is the true data set where
Yeah,
people come.
it's the true data set that we would be working on. That's
Um,
the case. Yeah.
okay. The other question I had was export masks. You already covered that you have DICOM exports and raw exports.
Yes.
The other question I had was that for MR images, does it work only on the PD weighted images, or do you also support T1, T2, 3D
We
DES?
We do support T1, T2, so that's there.
Okay.
Then we also have CT and MRI integration. So even if we need to do the registration, that can also be carried out. And then we also have one more facility that is virtual X-ray generation. So even if we are working on any CT data, so virtual X-ray can be generated around any coronal, sagittal, or axial axis, whichever is required.
Okay. Okay, that makes sense. That's all the
Yeah.
questions. Thank you.
So we shall be starting the live demonstration, ma'am. After that, also, if you need the access of the software, if you are facing any issues, I'll be just sharing my contact details at the end. You can contact me anytime. I will
Sure.
also share my mail. So any specific white paper or any other published paper that you need to check, I'll just share you the links. That's
Okay.
okay. Yeah.
Thank
Yeah. Thank you so much for the questions, ma'am.
you. Sure.
Has any other user used software?
I haven't used the software. I have used ITK.
Okay.
Simple Bar, I haven't used it.
Okay, ma'am. ITK Snap I am aware of, so I had used it in past. So you can
So it
start
will be
working on
helpful
Simple
if
Web,
you
ma'am.
can tell us how it will be helpful in surgical planning because we are having a project in surgical planning.
Okay,
So
so
it will
it's an
be
ortho
helpful.
set or cardiac set, ma'am.
Cardiac.
Cardiac. Sure, ma'am. I'll be
So
helping you out
yeah, we are
for
using cardiac imaging. So it will be helpful if you can throw some insights or show some demo in that one. Or later on also you can, if possible, if you can share some tutorials on that one, it will be helpful.
Yeah, ma'am, I will be sharing the tutorials as well. I had also created some model for some data set like VSD defect I had worked on recently for range study.
Okay.
So the particular patient had VSD defect, then I had only done the image processing and later on 3D printed model was created. So
Sure.
I'll be probably sharing that on the 8th session. So that's on 8th of August. I'll be demonstrating and focusing more on cardiovascular part, if that's okay to you.
Sure. I am looking forward for that.
Yeah, definitely, ma'am.
Thank you.
So, Pratik, you can continue with the live demonstration. Meanwhile, just show the basics. Hello, Pratik. I'm audible? Hello, Pratik. I'm audible. Yeah, you can start the live demonstration.
So I hope my screen is visible. So after opening the software, the interface looks like this, where we have the options to import DICOM images, and here like the recommendations are already here, which we have previously imported in the software. Here we can see the project information, and in the upper part, this is the tool ribbon which we are going to use in processing and segmentation of our image. And from here, we can get a tutorial from the software. This is the tutorial. Everything is written here. So if anyone having any problem, it is written here in very simple words. So now importing our patient data. So we just have to click on the file and new project and DICOM images. Since we are uploading a patient data, so we click on DICOM images. From here, we have to click on scan folder, and we have to navigate through C and then program files, and here synopsis, simpleware medical. Since we are using 2024 version, so selecting this and then going into data. Here we have a lot of patient data already available by synopsis. So from here we're going to take the pelvis data.
Sorry, Pratik, I'm interrupting just in between. So
So
the current version that has been released is 2025.06. That was the June release date. But in this particular system in which Pratik is showing the demonstration, the version isn't available. But at IIT Madras, I had already done the installation of the 2025.06 version. Why I'm highlighting that is the external models that I was talking of has been included in that one. So it was introduced in 2024.12 version, but there were certain improvements that were required that were carried out in the 2025.06 version. So Pratik, you can continue with your demonstration. This
sure,
was the
sure.
specific one. Yeah.
So this was 2024.12 version. So I'm selecting this and going into data, and we are taking pelvis data. So we just have to click on pelvis and select, click on this folder and select folder. It will automatically take pelvis data. Uh, here we uh, Here we can see the patient name, uh, and here other details are there, like manufacturer is Siemens, modality is CT, and other details. So from here we just have to click on the finish. Here we are seeing three 2D viewers and one 3D viewers. We can see our image is there, 3D image is there, but we can see a lot of artifacts and noise. So we need to pre-process this image before segmentation. So here we can see the project information. Let's go into image processing section. Here we have transform toolkit. We have resample, crop, and rescale, shrink wrap, pad, align, register dataset. So first, what is resample? So resample is basically used uh, to resample or downsample, like upsample or downsample the image. It is used when our data set is quite bigger, and it is also used to artificially increase or enhance our image memory or quality. So how it will become, like we have to increase the sampling parameters, so it will decrease, so it will downsample. If we increase the sampling parameters, it will downsample, and if we decrease the sampling parameters, it will upsample. So currently we can see here are 279 slices, here 239 slices, and here are 512 slices. If we upsample it, so we need to decrease the sampling parameters. So I'm currently putting it to 0.4, 0.4, and 0.4. So currently it is 68.7 MB. So we just upsample it. We made our data set memory bigger, and we can see like the slices are also increased. This like artificially enhance the image data. So now we undo it. So similarly we can do it for downsampling. So let's put it one. So now clicking on apply. So now we can see the slices decreased. So it uh, basically decreased the memory. Let's now let's undo it. Let's coming forward to our second part, that is crop. Crop can be very useful when uh, we can basically directly crop our region of interest. Like if there is any artifacts, then we can crop, and it reduces the size of this 3D image. So when we are done, we just have to click on apply. And this is the fast preview option. We just have to click on this after our every operation. So now there are many tools in this transform, that is rescale. Rescale is basically used to like increase or decrease its physical parameters. So it's basically increase its voxels or decrease its voxels. Next is shrink wrap. Shrink wrap basically it's the opposite of padding. So in padding, if our data has if our data is not having the specified canvas or like the region to work, so we use pad to increase uh, some amount of uh, canvas to work on. So it basically increased the area. So now let's coming into segmentation part. We are using threshold. So this is very useful tool to mask our structure. So we can manually set grayscale values from this histogram, but Synopsys Simpleware provides us the CT presets option From here, we can click on bone, and it automatically calculated its lower value, that is 230, and upper value, that is 3020. So now we just have to click on additional processing, which will help us in processing this image, and click on apply. So after applying, we have to click on this fast preview. So we can see our mask is ready, but it has some deformities, but our artifacts are gone.
I just have one point to add. So here the preset CT preset that we are having. So it's the default value whenever we install the software. These are the value that are automatically set. If we have certain data set parameters, the CT parameters, and we know the bone region would lie between 188 to 3000, so that too can be changed directly in the preferences section. We have the option of changing these presets. So next time when we'll open the dataset, bone Hounsfield units would be between 180 to 3020. And apart from that, that is particular one part is discussed that only keep the largest resulting island. So for example, if we are working on a femur region and if we don't want to separate it from tibia, so we will not be selecting this only keep the largest resulting island, because if the particular parts are disconnected, so whichever part is larger, it will select only those region. And again, coming back to the city preset, so over the top you can also see the histogram. So whenever we will be shifting up the histogram to the left, to the right, we can directly change the grayscale value. So yeah, Pratik, you can just carry on.
So now we have created our mask, so we can process it further. So since it is only one mask, we have not splitted regions of femur, hip right, hip left, femur right, and sacrum. So we can simply like select this option. It will basically fill the bone. Currently it is hollow, so it basically fills the bone and it solidifies the structures that help us in processing the image further. So clicking on this bone filling and click on apply. So this error is for this is for research purpose only. So we just have to click on yes. So it takes few seconds, but but it is usually faster than auto segmentation. Let's wait for it. Since we are using a combined mask, so it is taking some time to fill the bone. If we have used a different mask for different bone filling, so it might have taken less time. It also depends on the GPU of the system which this software is using. And now let's cancel it. It's taking a lot of time. Basically, it happened because like the dataset memory was high, so it took a lot of time. You can just again open it.
Excuse me, I had a question. Can I ask now?
Sure, sure.
Does the software by itself has any integration with any programming language, or is there any add-on that can allow for integration with a programming language like Python? Because 3 Slicer has that, and that is quite useful in research purposes.
Yes, yes. Like we have scripting option in which you can use Python.
Okay, so Python scripting is possible.
Yes, yes.
Okay. And what about the Python modules we use? Can we use all the Python modules that we use, like um, TensorFlow, PyTorch, and all?
Hello.
I was asking if we can also use the different Python libraries like PyTorch and TensorFlow.
Yeah, we can use the PyTorch TensorFlow that is using external models. We have the capabilities of that. So
Okay.
I think my system's working for now. I can show in my system probably. Just give me 2 minutes.
Yeah, yeah, sure.
Just give me a second. I'm connecting. I hope my screen is visible. So this is the latest version that I'm talking of. So actually there were some issues in my system. That's why I wasn't able to open the software. Now I will be taking over the session. So just give me a second. Yeah. So we were talking of the scripting options that we have to introduce our own sets of add-on. So that we do have. When we will go in the auto segmentation, so you can see there is an option of external models. But before that, let me import any DICOM data set. So since Pratik was working on a hip pelvis CT scan, so I'll be taking the same example. I'll be just going into DICOM images section. In the scan folder, when we are working in simpleware, we are provided with some set of sample database library that we can work the data from. So over here, we will be selecting the pelvis folder. When we have selected this pelvis folder, it will select out all the particular DICOM slices that are present in this data set. And if, for example, this being a case of orthopedics, so we generally don't deal with 4D data set in the case of orthopedics. But if we are having a cardiac data set and we need to work on a 4D cardiac data set, that too can be done. And we will be getting all the particular series that are consisting in our DICOM folder. Now, coming back to this, whenever we are importing the dataset, all the important DICOM data tags can be visualized over here. To keep the confidentiality of the patient in mind, we just need to click on this anonymized DICOM data tags. Once we have done this, we can also click on this remove file name from log. So all the particular important information that we need to hide, we can do in a single click operation. Once it is done, we just need to click on finish. Now, since we were talking of two aspects, the first one was the manual segmentation and semi-automated segmentation techniques that Pratik has discussed. So coming back to that part, to do a semi-automated segmentation, we can go over a threshold-based operation. When we have gone over the threshold-based operation, we will be selecting a CT preset. I always prefer a better approach, that is being a profile line tool. Why I say that? Because whenever we are selecting this profile line tool, we just need to select out 2 points. For example, this is one pixel that we have selected, and this is one another pixel that we have selected. Also, when we are hovering on any 2D slice, for example, currently we are checking the 128th slice in the coronal view. When we are hovering on to certain points, so you may be seeing some values in the bracket followed by one another value. So these are basically the x by z coordinate of the specific point in the corresponding to the 3D view. Also, the 183 represents the exact grayscale value of the specific point. So whenever we will change over here, so you can see the grayscale changes accordingly. So coming back to this part, why I have used a profile line? Because the profile line tool is the best tool while we are working with any threshold based data. So to identify grayscale variation, this is the best tool that we can use. Here, whenever we have marked the two different points, so we can see there is a lowermost grayscale range that is occupied. It's around 221 and uppermost being around 897. So when we will write around here 897, I'll just take a little higher up value 900. So you can see the all points that were in between got covered. So we can have a better idea about the data set that we are having. So this is very helpful while we are dealing with any soft tissues, because soft tissue identification is quite difficult. And anyone who has worked in the soft tissue segmentation, for example, segmenting heart out, we know how much difficult it is because there are nearby artifacts, there are also metal artifacts, some bone parts also get identified. So this is one such approach that we can use. There is one more best approach while we are dealing with soft tissues that I'll be showing in the session that is being organized on the 8th of August. So since that is focused on the cardiovascular and the vasculature part, so I'll be showing that in that session. Now coming back to this part, we need to click on apply. Once we have clicked on apply, as shown, it will create a good mask for us. All the small islands that are present in the dataset gets removed. Since we have clicked on this, only keep the largest resulting island. Once that is conducted, we just need to click on refresh and we can obtain our mask that we have selected out. Now, the next task being is to split out this particular whole mask into different regions that are being present. Why we say so? Because, for example, if we have done a whole threshold based segmentation for a whole pelvis data set, but we only want to work on the right hip or the boundary region connecting with the right femur, so we might not be interested in all the other parts. Similarly, if we are doing any sort of 3D printing, if we are doing colored 3D printing, that too can be done in an easy way while we are dealing with this sort of approach. So to segment and split different parts out, what we generally do is we have a split region operation. In this split region, we are given with certain presets for orthopedics and cardiovascular data set. But for example, there are some data set that doesn't have the preset present. For example, if we are doing a kidney segmentation, we need to segment out the kidney cyst from the whole main region of kidney. So we can also click on add region and add the specified region if not present in our preset. Presets are very helpful while we are marking out different regions. For example, if I'm just selecting a hip, all the orthopedics part in the hip gets highlighted, the major orthopedics part that are present. So now what we need to do is we need to set out the boundaries. Setting of boundaries is also an easy task. We have two options for that. Either we can mark up the boundaries in the 2D view, or we can also mark up the boundaries in the 3D view, whichever is feasible and whichever we are comfortable with. For example, let me take a sacrum. I'll be just going on to 147th slice over here. Since I have worked with this data set in past, so I am familiar with the number of slice that we need to work on. So here we can see there is a proper boundary segmentation that's separating the sacrum from the hip bone. So what we generally do is we can either mark the region over here but we need to be very careful while we are marking so that the other regions don't get covered. So I generally prefer a better approach, that being to directly mark in the 3D, because we will be free of any wrong markings. We can directly visualize how the marking looks like. And this works on watershed algorithm. So whenever we are splitting up different mask from a whole single part, so it uses nearby watershed algorithm to check out the grayscale variation, and at the boundaries, it just splits up the following part. To do the particular set of operation in 3D, first we need to do is we need to toggle this live 3D mask preview. Once we have toggled this particular button, it's very important, because now whenever we will be starting marking the region, so you can see one region got highlighted. So I'll just go over here. I'll remove the selected region, marking up the boundaries from start, taking a hip reset. Yeah. Now I have done this. Now starting up with the marking of boundaries. So what we need to do is, for example, I have selected sacrum. I just need to highlight the region that's separating the particular right hip from the sacrum, so we can mark up like this directly in the 3D. We don't need to rely on the 2D parts. And similarly, we will select over here. We can mark it up over here. Now, we will be selecting a hip left, selecting again the boundary, and the control in simple way is quite easy. We can just directly work on the specific hour. We can highlight the boundaries in a fraction of seconds. We just need to select out the boundary highlight region, and now rest task would be done by software itself. Also, if some region gets captured in the other part, so that too we are given with an option of refinement further, so we can use region growing and other tools once we have done the segmentation. Similarly, we can remove, so we can do the shrinking of any part if extra part has been selected out. So we need not to worry if some part gets captured. For example, some region of a hip gets captured in sacrum, we can easily do the splitting for the following parts. Once it is done, I'll again mark the boundary over here. This is how the boundaries are being marked. We just selecting over here. Oops. So I'll just undoing this. So to undo any operation in simple way, it's the same set of keyboard stroke. So it's control followed by Z, through which we can undo any operation. Once this is marked, we will also mark the left femur and right femur. So I'll just show directly. We'll be selecting like this for left femur, now right femur. Once this particular part identification has been done, the particular splitting operation has been performed, we can just select a preview to check how our output would look like after the particular splitting has been performed. Once we have checked the preview, we can see, and if we are satisfied with the particular splitting, we just need to click on apply, and it will just start the process of splitting it into various parts. Now, once the segmentation has been completed and we need to further split up we need to work on the specific parts. For example, if I just need to work on a hip right, what I can do is I am given with further multiple options. When I'm just right clicking over here, I can rename this part. We do have option of using Boolean operation. So for example, if we need to combine two different masks, the right hip and the right femur as a single part, that too can be done. If we need to subtract some region, that too can be carried out. Union intersection can be carried out. So there are multiple options that we can further work in the Boolean operation. Here we are given with two sets. Either we can use this sets of operation, or if we are familiar with the Venn diagram, so through that also we can apply the Boolean operation. Apart from that, since we have done the segmentation for a hip right, if we need to export this particular part out, so I can select the series number, I can do the exporting, and I can export out the particular dichrome data set for the splitted part. Now, other options that we are having is to change the opacity. So for example, if I need to decrease the opacity, first let me generate a fast preview so that the small gaps that are present are being removed. Since we have decreased the opacity in the sacrum region, so you can see how the particular parts have been highlighted out. And if we further reduce down the opacity to somewhere around 0.2, we can see a translucent surface over here. And we can basically see the internal structures of any part while we are reducing the opacity directly while we are working with the mask. So this is one such approach. If we need to just work on any specific part, for example, hip right, what I need to do is I need to right click over here. Here we have an option of isolate. So it will isolate this particular part out and we can work on the selected region. And there is one more extra part that it has selected out. So what we need to do to remove our search region is we need to use a mask flood fill approach. When we will use a mask flood fill approach, as it was discussed in the presentation, so we are given with two sets of operation. The first one being the flood fill operation and the other one being the inverse flood fill. So let me show how both the particular parts work. Before to show that, let me create a copy of this so I can just click on duplicate and it has created me a copy of this particular mask. Now, while I am working with an inverse flood fill operation. Now, whatever small island that are being present, if I'll be clicking on this particular part, so this particular part would only get removed and other small islands that are present in the nearby region, we need to remove it separately. So this is how the inverse flood fill works. But a better approach to deal with large structures is to use a flood fill based approach. When we have generated a mask preview, we need to select out the operation as flood fill, the mode as 3D. Once that is done, let me take the active mask as right hip. We just need to select any part over here and all the disconnected region gets removed. Now, our next task is we have done the segmentation, we have isolated this part, but if we are working on any 3D printing part, we need to do the solidification, how that can be carried out. So to do that, we have a single click operation known as bone filling. So it automatically solidifies bone, checking the nearby grayscale region in mind. So whenever we will click on apply, clicking on yes, it will take around 2 to 3 minutes for the process to be completed. And it generally depends on the part that we are selecting of. If we are selecting a smaller part, so the particular processing time is quite less. But on an average, it takes around 1 to 2 minutes for smaller parts, and for larger parts, it takes around 3 to 4 minutes to do the particular bone filling procedure. And the estimated time remaining is just for our visualization. Once the process gets running, it automatically recalculates the time that is required. And once that is done, it has solidified the particular bone part for us. So we can see the resultant changes in the particular 2D view. We can also check the contour levels that it has filled up. So if we need to check the 3D contours, that too can be done. That is one such possibility. If we are comparing it with over here, so we can see all the particular blue region that is getting highlighted is the particular filled up region. Sorry, yeah. So all the particular region that is getting highlighted is the filled up region that we have solidified using the bone filling operation. Once that is done, we can also check the resultant surface changes. So let me just obtain this particular mask. Now, there are a lot of noises that are being present in this data set. And when we are coming on to the boundary, so some region of the boundary also are not properly marked. So what we can do is we can go over here. We have various filtering options. We have various advanced filter tools. Over here, we can use, for example, if you're working on an MRI based data set, we need to do bias field correction. That too can be carried out. If you're working on a CT correction, that can be selected. Any metal artifact reduction can be done. Direct smoothing and noise removal can be done for DICOM itself. So even before starting for the segmentation, we can remove out any noises that are being present. If we are working on any center line network measurements, we can use this particular skeletonization tool to prune the particular center lines that we are working on. Then we have the mask similarity calculator to check the similarity between different masks and different operations. And there are various other tools that are being present. To tell about each and every tool in a single session is quite difficult, but we have a better approach for that. So for example, if I need to learn about this Laplacian of Gaussian filter that is present in simpleware, what we need to do is whenever we are opening this particular window, corresponding to every tool that we have a question mark sign. When we will be clicking on this question mark sign, a direct link up is there with the tutorial guide, and we can go to the specific point and understand what algorithm is being used behind any tool that we are using. So this is the best way and the best approach to learn about the software, to go inside the tutorial guide, to check for any specific part that we need to work on. For example, to start up with any image processing, how we are doing that, what are the pre-processing operations like transformation, alignment of images, resampling, rescaling. These two can be covered out from this particular tutorial guide in a very easy and efficient way. Whenever we are working with any 4D image dataset, how to import the dataset, how to use the frame toolbox to see the particular life changes in the dataset, that too can be done. So this is a very great tutorial guide that comes directly with the software, and anyone who has the access of the software can go through this tutorial guide. Now, coming back to this particular part, we were dealing with how to deal up with this local surfaces that have been created, or how to do local surface correction. For that, we have this local surface correction tool. Here we have two sets of operation. Here we can select a search radius, so it will search the radius nearby to the particular pixels. So corresponding to each and every pixel, it will be defining its correction settings. And now this is the smoothing radius that we require. And generally a value around 1 to 2 is recommended for using the smoothing radius, as the more higher the value, it might distort the particular workspace that we are working on. So taking a default value of 1 and 1, I'll be just clicking on apply, and let us see how the particular resultant changes looks like. After every operation, our mask gets out of date, so we need to click on this generate a fast preview, and we can see it has done pretty decent job while marking up the region. We can also check out the surface correction over here. It has marked up the boundaries very clearly. But there is one more need to check for the accuracy and whether how accurate our segmentation is. So we have two sets of operation. Either we can go with an auto segmentation. Here we can do the auto segmentation from HIP revision CT, or external models like UNet models, Bonai models that can be selected out. Total segmenter from 3D slicer can be imported. So we have multiple options in the external models. Even if we are integrating our own sets of segmentation algorithm, that too can be directly be done. We can just click over here, we can select up the particular part, and we can directly do the selection. Is my screen visible? I think there's some delay between my screen and my voice.
It's mostly in sync, Ayush. We can see both your screen
Okay.
and we can hear
Okay.
you.
Actually, in my mobile phone, so it was not that clear. So thank you for this. So coming back to this external models, this is one such important tool that has been introduced. To learn about this tool in detail, we can go over here. How to integrate our own sets of algorithm in simple way. So that too is explained using the GUI. So we can go over here. For example, if we need to work on Monai models by NVIDIA, that can be done. Any NNUNet model bundle can be directly selected, total segmenter. Then we also have the simple way auto segmentation tool. Now, the most part being how to have our own sets of API creation. So what we can do over here, we have a full detailed tab. When we will be opening this, we have the class list through which we can create our own set of script for doing any set of algorithm generation. That too can be selected. We can also check from these examples how to basically operate on the software. And apart from that, we also have various command tools. So even if we are not using the GUI, if we have created our own set of Python file using its class list, and if someone's new to scripting, they can check over here how basic our own sets of plugin, how the particular plugins work. So this is how we can integrate our own set of algorithm over here. And later on, this is one such way to check out the accuracy of whatever part that we are working on. The other way being to check the initial accuracy, what we can do is we can overlap the particular mask that is being generated with the DICOM dataset itself. So initially, as you had seen, once we had imported the dataset, there were three views: coronal view, sagittal view, and the axial view. And apart from that three views, we also had one more view, that was the 3D volume rendering of the dataset. And at that time, we didn't had any mask to be created. So at any point of our workspace, we can again bring that particular volume rendering. And once we have brought out that volume rendering, we can go over this option, configure this background volume rendering. And here we need to select option of masking. So if we select a hip mask, right, selecting out this mask, so we can check the accuracy of the segmented part that it has created. So corresponding to each and every contour, corresponding to each and every level, we can see some part is getting highlighted more. So what we can do is we have one such option to go to the specific point from the 3D view directly to the 2D view. What we need to do is we just need to click on the left button in my mouse, followed by the P keystroke in keyboard. Once we do that, so for example, I am going to the specific point over here. Sorry, I'm just resetting my view. So we can reset the view in any direction. So this is the standard view that we get. We can use R key in our keyboard to reset this view. Then we have the X view to change the particular view. Similarly, we have Y, we have corresponding to Z view. Then we also have the different alternatives, the mirror views of the following. So any view can be selected corresponding to which part that we are working on. Now, now talking of the specific point, how to go to the specific point, we just need to click on left, followed by P keystroke, and you can see the particular slice intersection goes to the specific point corresponding to the point that we have selected. For example, in all the three views simultaneously, so it has all automatically shifted the number of the slice to 192 slice in the sagittal view, to 47th slice in the coronal view, and to the 101 slice in the axial view. And corresponding to this, it shows that this particular point has the particular point that we were selecting. And we can see there are still some corrections that can be done. To do some sort of small modifications, what we can do is we can click on this Smart Paint tool. When we are working on this Smart Paint tool, we can use this algorithm. So what it does is we can set out a value from 0.01 to 1. A value around 0.5 to 0.7 is generally recommended to mark out the nearby region. So what it does is, for example, this particular point that I am highlighting out is a grayscale range of 378. So it takes the 70% of the nearby grayscale, so from taking a value between 300 to 400 and the nearby grayscale region that lies. And when we will click on Smart Paint, it will highlight the region that lie in the particular grayscale range, and it will mark up the following. For example, if we are just clicking over here, since this particular part didn't lie in this particular grayscale range, so it didn't get marked up. But if we will slightly increase the grayscale range over here, and if we start marking the region, so what we will do is we will be getting the specific grayscale region to be collected out. So we can our general recommended value while we are working with a medical data set is between 0.5 to 0.7. But for research purposes, we can alter the values to see how the resultant changes looks like. These are the normal modes of operation that we have in the local surface correction. But you can see there are certain small islands that have been created. So this was the paint region that I had used, and a small island got created. To remove this island, we have two options. Either we can again go to the mask flood fill operation to remove the small islands, or we also have one more option of the 3D editing button. In simpleware, we are provided with two modes of operation. One is simple 3D editing and another one being the advanced 3D editing. When we are working with the simple 3D editing tool, we have multiple options that can be worked on. For example, the delete operation, whichever part that we will be selecting will get deleted. So we have multiple operation tools, like we can select a region as a rectangular region. We can also select a polygon. So for example, I'm just taking small parts to show in a singular region. So this part light in this particular polygon, so it got removed. Similarly, if I mark up this sphere, I remove this particular part, I need to go to the specific point, marking this particular region. But the best mode that I always use is the lasso, because it's a freehand move. We can have the drawing in any direction, and we can remove all the particular disconnected parts that are being here. Apart from our delete operation, if we need to do the closing operation, so to bring two pixels together by a significant amount, so I can go over here, I can just select on close, and it will bring the particular parts closer by the specific strength that we are selecting. So over here we have a strength value selected from 1 to 5. But if we need to further increase the strength value, what we can do is we can go over the close operation, and then the operation will be applied for the whole mask at once. We are also given with alternative options. So what we can do is we can go in this 3D editing only. We can use a smoothing operation, applying the same set of result on the same part. Why I'm showing on the same part, because you will be able to see the resultant changes while we are applying different sets of operation. So this being one set of approach, how we can smooth out a specific part. But what if we need to smooth out the whole part at once? So for that, we have multiple smoothing filters, starting up with the recursive Gaussian. Yes, ma'am. Do you have any query? So if you have any query, you can interrupt me. So coming back to this particular smoothing filter one, we have various options. So we have the recursive Gaussian, then we have a mean filter, median filter, then smart mask smoothing, and the de-stepping one. So for example, if we are working with a recursive Gaussian one, we can go over here in the recursive Gaussian, and then we can just select the particular part out. We can select out the strength value. So for medical cases, value the uppermost value that is recommended is 3. We can use the particular value strength. We can click on apply and it will automatically smooth out whole part for us using a recursive Gaussian filter. So this is one such approach while we are working with any part, how to deal up with part directly. Now, since we had worked on this hip right segmentation, now there are various other tools that we have. We have the measurement tools that is a complete bundle in itself. So we have the starting tools right from small measurement, and we have a wall thickness tool. So to check out the wall thickness corresponding over here, we can also annotate the minimum and maximum enable probing from here. All the statistical report can be exported out as a CSV file or a text file, whichever is selected in our exporting mode. So these two particular values can be selected in the preference section. Whenever we will be clicking on this annotate minimum and maximum enable probing, we will be checking out the specific point corresponding to which the value is minimal and corresponding to which point we have the most thickness in this whole set of masks. Then we have the 2D contour calculation. So if we are working on any 2D view, if we need to check out a specific area corresponding to our 2D view, what we can do is we will be just going over here. Here we have multiple options. Here we can use a polygon one where we need to set out the different points corresponding to the surface. We can have n number of points to be selected out to have the most precise of calculation to be carried out. Once it is done, we'll mark the particular region. Yeah, so once it is done, we will be getting all the particular corresponding values over here. The total area that it is acquiring in this particular part, total perimeter, the in-circle diameter, the out-circle diameter. We can check all the particular 2D contour statistical report from here that can be exported out to. Apart from this, we also have other measurement tools like center line network tool. Uh, I think the center line network tool will be much more helpful when we will be covering out the vasculature structures, the particular cardiovascular structures. So that can be shown over there. Then we have the mass similarity calculator to check out the comparison between two similar masks. Apart from that, in the quick statistic, we have multiple options. We have a volume to check out the direct volume of whichever active mass that we are working on. Then we have the particular surface area selection to check out the whole surface area of the selected part. We can also check for the volume fraction corresponding to whole part. So it also takes the vacuum spacing in mind. But to check out the specific volume fraction for this particular hip right corresponding to this whole hip, what we can do is we can go in the mask statistic and we can generate the statistics of all the active mask. Once that is done, yeah, so hip right was selected. So let me select other parts as well. Or one more thing that we can do is we can directly click on general statistics. It will generate whole statistic for corresponding to each and every part that we have worked on. So all the specific values can be checked out from here. Then we have the template library. Here we can edit out this template library. We can set out any sort of template while we need to how we need to operate this particular statistical template. So that too can be selected. Any part can be selected. If we need to add up any specific information, that too can be checked out. So we have full editing options over here too. We also have the user defined one. So if we need to create any specific set of template for our specific requirements, that too can be checked from here. This being the statistical tool, all the rest measurement tools I'll be covering in the next session, I shall also be checking out the particular surface tool, how to import any surface, how to place up the a particular implants if we are working on any implant, how to place up with the segmented part to show in a brief. So when in our example dataset library, we also have an acetobular cap implant STL file. Whenever we are importing any STL file, any PLY file, step file, IGS file, all the particular CAD formats are supported in Simpleware. We can check the information about the file from here, the total number of polygons it has, the total number of points it has, whether the particular STL file that we are selecting is watertight or not. That too can be checked. Any self intersections can be checked, bed orientation can be checked. And if there are any sort of error that are being present, we can just click on this fix option to directly fix up any specific part that we are working. Once that is done, it brings the particular implant in our view. But before processing, we need to first bring it to zero position, that is at origin. Whenever we will click on this zero position tab in the surface tools option, we need to click on apply and it will bring out any surface file. For in this case, it is an acetobular implant at 0 cross 0 comma 0 position, that is the origin position. Once that is been done, we need to check the position and orientation, and here we can do the interaction in both the views. Either we can mark up the boundaries in the 2D view, we can do the particular placement in the 2D view, or the same can also be carried out in the 3D view. So all the particular operations can be performed. So if we need to directly do the positioning in the 3D view, that too can be done. We also have an additional option to do registration of data sets, wherein we can register the two different data sets. So if we are working with two separate surface, so like this, an easy positioning can be done within couple of seconds. Once this particular positioning is done, whatever are the intersection points, we can check that out. And later on, it can be exported out as a single model for doing any sort of FE analysis and all. These all sections, the FE analysis, since the basic segmentation has been just told in this session, and it's quite difficult to accommodate whole training of Simpleware in just 2 sessions. But I'll try my best to basically facilitate the same. In this session, just the basics of the image segmentation, how to do that were told. I'll just show one more feature, this that is being the auto segmentation. So here we have the hip revision CT. Here we have an option of keep all bone fragments and output femur cancellous bone. So we need to separate out the cancellous bone, even if the particular is the post-surgical data set that we are working on, if it has implants, so the software has the capability to segment the implant out from the image data set that we are working. We just need to click on apply and the process would work. But before that, let me just create a new separate folder over here to highlight the manual segmentation difference from the auto segmentation. I'll just select manual and I'll just drag and drop all the particular parts. So this way the things get sorted and it looks, the GUI looks very clean. So once we are starting with auto segmentation, we need to click on apply. Generally for auto segmenting such data set, it takes around 2 to 3 minutes. It also depends on the GPU. So earlier on, in which the system in which Pratik was demonstrating didn't had any GPU. It had the integrated Intel graphics card, but the system that I am working on has RTX 4060 GPU. So you will be seeing the difference. In that system, it will take around 45 minutes, 1 hour to do the same segmentation. The same segmentation in a GPU enabled system gets completed in within 2 minutes. Less than 2 minutes to be precise. So the process would be completed in less than 2 minutes. Once the segmentation has been done, we can directly work on the specific part. I was talking of the measurement. So whatever plus points that you are seeing are the key landmark points that the software automatically highlights. Once these particular key landmark points are highlighted, we can go to the measurement. For example, if we need to do the measurement from a left femoral head to right femoral head, we can directly select out the points once the segmentation has been completed, and the measurement can be done in a very easy and efficient way. So it will take another 20 seconds for the process to be completed. Let it complete. Meanwhile, till here, if anyone has any queries, please you can unmute your mic and ask the particular queries. Meanwhile, the process has got completed. So what I was discussing in the measurement section, all the specific important points, the key landmark points that have been marked over here, corresponding to that the measurement can be checked. So once it is done, we will get a summary tab corresponding to this summary tab, we can check whichever particular parts it has identified, which parts were not identified, unidentified. We can also check what are the key landmark points that it has highlighted. Once that is done, we go over to the measurement tabs, and now we will be having a full set of measurement option. And this is how the auto segmentation looks. So you can check over here how the auto segmentation is looking. So let me just toggle the visibility off for this whole mask to show the auto segmentation one. So this is the auto segmented part. So we can have the accuracy of the manual segmentation equivalent to the auto segmentation one. It takes generally time and practice while we are working on the software. Apart from that, if we need to isolate this out, sorry, I toggled the visibility. I just needed to isolate that. Yeah, so this is the auto segmented generated output. You can see all the key landmark points that it has selected. So it's femoral head, corresponding to this femoral head, what are the XYZ coordinate value, what is the grayscale, that can be checked out. So this is the normal functioning. Then we have the option of visualization of X-ray. So virtual X-ray generation can be done. We just need to click over here, set out the opacity saturation. For example, if it is a pelvis city, I'll just try to pass pelvis city over here, and we can also set out different presets over here. Then we can also check a particular orientation from here, coronal, sagittal, axial, and orientation level can be set, and the particular X-ray can be exported out as a PNG file. So this is just the basics of the more detailed tool. We won't be having any presentation of in the 8th session, the session that is being organized on 8th of August. So we will be directly working on the software part. Meanwhile, since you have one active license of Simpleware, so what you can do is you can start using the Simpleware at your end. And if there are any queries at any point, I'm just sharing my contact details in the chat box so anyone can ask. Meanwhile, are there any queries till now? You can just let me know. I'm just sharing my contact details. I'm also sharing my mail ID. Yeah. So any queries till here?
No queries from my side. If students have any more queries, they can probably share. And thank you, Ayush. I will email you as well.
Definitely, ma'am. Also, I will be sharing you the papers probably by tomorrow. Tomorrow
Okay,
afternoon,
sure.
I
No
shall be
problem.
sharing. Any more queries, anyone?
I think we don't have any queries. Thank you. It was an insightful session. It was informative also. We learned a lot, and we are looking forward to learn a lot from you during on the eighth session also. So, if you have any
Sure.
doubts, we will email you.
Definitely, ma'am. Definitely. Okay. Thank you everyone for
Thank you.
joining.
Thank you.
Thank you, Srinath sir, for organizing the session. Yeah.
Thank you, Ayush. Bye. Thanks, everyone.
Shall I end the session?
Yes, please.